Okay, I think we can get started. So hello everyone, welcome to SE seminar series. I hope you had a great holiday. And I'm John, the seminar coordinator. Together with me is Miss Kathy Medney. Kathy and I will be today's moderator. Our Associate Director, Rob Ferrero, also joined us, and he will be introducing the speaker. And just so you know that the seminar is being recorded, and we will publish the video on our YouTube channel. It usually will take a couple of days, so please feel free to check it out. And today we are very excited to have our speaker, Jeff, joining us from Illinois. And before he gets started, our Associate Director to introduce the speaker. So Rob, please go ahead.
Yeah. Thanks, John, and welcome, Jeff. Jeff's the the chair of the Department of Atmospheric Sciences at the University of Illinois, and his research focus is on severe storms and their impacts to society and the hazards that they create. And Jeff's got his degrees in atmospheric science, most recently at the University of Oklahoma. And he's also spent time prior to his current position working at the National Severe Storms Laboratory in Oklahoma and also at NCAR. And so I look forward to this talk. I know in our local area here in College Park, we've had some, seems like it's an annual event of some very damaging storms that have hit our area, which never used to happen as frequently as they do. So look forward to hearing his talk. So welcome, Jeff.
Yeah, well, thanks, Ralph, and thanks, John, for the invitation to be with you here today. And indeed, as Ralph, as you just mentioned, one of the motivating factors is a plot like this. So this is a trend that's put together from NOAA. This is showing billion-dollar disasters, inflation adjusted over this period. And I started doing this work back in the early 2000s. But if you look at just the last 10 or 11 years, one striking thing that you see is an increase in here over this particular period, 95 severe convective storm events. And this is only showing severe thunderstorm events produced over $1 million with damages. And most certainly, this trend is due in part to increased exposure, population density, more people, more buildings, but potentially also to anthropogenic climate change, or ACC. And indeed, like events, Ralph, that you've experienced and events that we've experienced over these past several years, I am commonly asked these questions by reporters in the wake of such events. And this serves as part of the motivation for my work as well. So as an example, was this event caused by climate change? Will severe convective storms and their hazards, including hail and tornadoes and damaging winds, become more frequent because of climate change? And then lastly, will climate change make severe convective storms, and again, hazards such as tornadoes, hail, and damaging winds more intense? Well, if we have time, I can explain why question number one is a non-starter. But question number two, and that's going to be a focus of some of the talk, is something that I feel like we've made steady progress over the last couple decades, including work that Tony Del Genio and our group have done in 2007 and onward. Although, as I'll show, it's by no means resolved. And then finally, question number three, which is about intensity, is particularly vexing to me, especially with tornadoes. So both of these serve as motivating factors for this work. And indeed, for this talk, I'm going to spend maybe half talking about frequency, and the approach that we're going to take includes what I'll refer to as an implicit or an environmental approach that involves the use of environmental proxies. and then an explicit approach that involves high resolution or convection permitting dynamical downscaling. And then the third question, this question 3, which regards intensity, I'll focus on an approach that we've qualified as event level pseudo global warming. So here we go. One of the things that you'll see throughout this talk is there's a common thread of compromise, and each one of these approaches involves some kind of compromise. None of the approaches are perfect, and what we're trying to do is stitch the results together to come up with a convincing and coherent argument. This is not what I'm going to talk about necessarily, but I do want to give you a sense of why we're jumping into using models, because this is a model-focused research project. And so you should be asking, well, why don't I just use the historical data? Why don't I look at trends in the historical data? And we've done this, and others are doing this, and these approaches are valuable. But the one point that I want to make about using historical data is that for us who do research on severe convective storms, our data come mostly from eyewitness reports. So as an example, there's people that are in the field that serve as storm spotters. And so they will see a tornado, or they will see hail, or even see damage that's caused by non-tornadic winds. They'll report this to the National Weather Service, or somehow it will be communicated to the National Weather Service, and the National Weather Service collects these reports and makes these available as displays through the Storm Prediction Center and also through NCEI. And so, as you can imagine, there's all kinds of potential issues that go with using the historical data, in particular these reports. But it is possible to use these, and so this is just an example of how one might use these, and they're used judiciously as an example by a days methodology. So here, these are tornado days, which tend to be less sensitive to reporting biases. And so this is a time series of the probability of a EF or F scale day over this period, 1990 to 2015. That's in the green. And what we've done is separated this by the early part of that time period, which is in blue, and the later part of that time period, which is in red. And what you'll see is that there's differences in these 2 decades, especially during the warm season, that the overall probabilities are changing in time. In particular, those from 1990 to 99. If we went back farther in time, this would even be more dramatic, or much less than from this period of 06 to 2015, except in December and early spring. And you'll see that that's a pervading theme in a lot of the work that we're doing. Okay, on to the modeling. So as I mentioned, I wanted to spend some time talking about this question number 2 about, is climate change causing more frequent severe convective storms? And so we should be asking now, if we want to do a modeling kind of approach, how do we address this? Can we use GCM outputs? And the answer is yes, even though convective storms, which normally have length scales on the order of tens of kilometers, are going to be unresolved in GCM grids of 100 kilometer or 50 kilometer, or even 25 kilometer spacing, we can exploit the fact that these convective storms are strongly controlled by their 3D environmental. And when I talk about environmental, I mean their near or pre-storm conditions, especially temperature, humidity, and winds. And these define, and we can define proxies based on this information. So apologies for those of you who are very familiar with these concepts, but for the sake of a broader audience, I thought I would mention that there are 2 parameters that represent well the potential for severe thunderstorms. The first is known as convective available potential energy, which I'm going to abbreviate as CAPE. And the other one is a form of vertical wind shear. So here, this is the magnitude of the vector difference between winds at 6 kilometers, which is basically the middle of the troposphere, and the near surface winds. I'm going to call this S06. There are other ways of evaluating vertical wind shear, but this one seems to work pretty well for the types of phenomena that I'm interested in. And so in our schematic, a vertical cross-section of a convective storm, we use CAPE because this sets the theoretical maximum updraft speed. So the basic idea here is that the larger the CAPE, the larger the maximum updraft speed. And the vertical wind shear, this S06, this helps organize updrafts and downdrafts, as well as provide a source of rotation, which then affects the storm dynamics. So both contributing to rotating storms as well as their longevity, which are in turn related to this rotation. So we can take these two parameters in particular and analyze these using vertical profiles within GCM output, just like what we would do with observed soundings, and do these on grid point basis and come up with something like this. So this is a paper that I did with Noah Diffenbaugh and Scherer back in 2013. So it's a bit dated, at least the paper itself, but the results, as I'll demonstrate, are still robust. This is just showing changes in CAPE and vertical wind shear. And here, where I'm showing is future. So we have a 30-year future period relative to a 30-year past period, historical period. And the warm colors represent increases, the cool colors represent decreases. And on the right are the 4 seasons. And what we see, which is consistent with basic physical arguments, is an increase in the mean CAPE over these different seasons, with the biggest increase over the summer season of June, July, and August, but also throughout the warm season, and a decrease of this vertical wind shear over all seasons, but especially during the cool seasons. As I mentioned, these are consistent with basic physical arguments. This is essentially a thermal wind relation argument where the north-south baroclinity decreases owing to more warming or relative more warming at higher latitudes. The response in the vertical wind shear should go down. So what we want to do then is combine these in a way, and we've combined these in essentially a product between the two, and we call this ND-SEV. This is our proxy, and what this shows when we combine these, again, thinking of future minus past, is a robust increase in the future number of days supportive of severe thunderstorms in the US, especially in March, April, May. So we want to view this as the number of days that would be supportive of severe thunderstorms, not the number of days in which we see severe thunderstorms themselves. Once again, I want to allude to this, that even though when we look at this proxy, that the magnitude of the change is the largest in the spring, the largest relative increase occurs in winter. And that's something that we've certainly been seeing even over the time period between the current time period and when we published this paper. So I mentioned that this is not a perfect approach. It has advantages, and the first advantage is that it can be readily implemented using 3D subdaily climate model output. And I have climate in parentheses because these types of proxies, or at least the parameters, are also shown in day-to-day numerical weather prediction products, but increasingly also becoming available in reanalyses and also in climate model output. So whenever we have three-dimensional, and subdaily is key here, because what we really want to be able to do is separate and analyze these during times when at least the model would present a maximum in solar heating. So it would be important to have subdaily data. So that's a benefit, and so we did this using CMIP-5. We're working on a project right now using CMIP-6. We've done this with regional climate model output and so on. So this is pretty easy to implement, and so whenever these are available, we can do this approach. The key point for us here is that this provides for ensembles and therefore measures of uncertainty. And so we were able to say with a Diffenbaugh paper that these are robust changes and based on a 10 model ensemble. The disadvantage is that this only tells us the potential for severe convective storms. So these parameters, CAPE and vertical wind shear, and even others, they don't predict convection initiation very well. So they don't guarantee that storms will actually form. And so we view these as upper limit estimates. So the numbers of days that I showed and their changes would represent upper limit estimates, and then something less than that or equal to that would be the actual numbers of days where storms actually form and then realize these conditions. Well, there is another approach, and the other approach that involves modeling anyway is dynamical downscaling. And we can use this approach of dynamical downscaling to address this second question on frequency. And in particular, if the downscaling model is run at grid spacings on the order of 3 to 4 kilometers, which are considered convection allowing because they preclude the need for a convective parameterization scheme. This removes the convection initiation issue that I just mentioned because these storms are explicitly resolved within a convection permitting model. What this also allows us to do is address specific thunderstorm hazards. So you'll notice that in the previous section, when we looked at these environmental proxies, we just used a generic term of severe convective storms. But now we can start to drill down and talk about specific perils, so hail as an example. So I want to give you an example of how we use convection permitting or convection allowing dynamical downscaling to address hail frequency. And here we're going to use a model predicted variable, a grid resolved variable hail mixing ratio to actually say something about this. And this is some work that we published in Journal of Climate a few years ago. So we use WRF, and this is based on work that Kim Hugoin did for a PhD at Purdue. What she used is WRF 3.6 at the time, and dynamically downscaled GFDL-CM3 under RCP 8.5. So this is all CMIP 5 era data. She also dynamically downscaled the historical time series. These are 30-year series of WRF integrations using 4 kilometer horizontal grid spacing. And so therefore they fall within this range of convection permitting or convection allowing, and therefore preclude the need for convective parameterization. And these are over the contiguous US. They also represent 30-year time series. So this is great for our statistical analysis in both of these. And these are also done over the entire year. So we're able to look at potential changes in seasonality as well. So as I mentioned, this is focused on hail. So before we get started, we want to see whether or not the model representation of hail frequency is in at least some agreement with the observed hail frequency. And remember that there are issues with reporting, and hail in particular is a tough one because, as you can imagine, hailstone falls and it starts to melt, and then maybe then it's reported, or it falls in a location that's not reported. So the analyses of hail reports are heavily smoothed, and that's what I'm showing here on the right. And this is the downscaling perspective based on the years that were available for this analysis. So in terms of the magnitude of the reports is damped relative to what we see in the downscaling results, but we have basically the right geographical distribution. So that's enough to give us confidence to move forward with this analysis. So what we've done is, and there's a lot kind of hidden behind what we're showing here, and I invite you to have a look at this paper for the details on how we convert a model predicted mixing ratio to a hail size. But nonetheless, we're breaking these into 3 different size categories: a moderate hail, a large hail, and a very large hail category. I think the moderate is 20 millimeter diameter, the large is 35 millimeter, and the very large would be 50 millimeters. And so I'm showing these going March, April, May, June, July, August. And these are hail days. So every day at a specific grid point in which we meet this threshold per the categories that we've defined. Warm colors represent increases, cool colors represent decreases, and these are averaged over the 30-year time period, both in the future and the historical. And what we see is that as we go from March through May, there's an increase over most of the eastern half, or even eastern 2/3 of the U.S. And this is the largest future increase of area. This occurs in May, and then we can go more in time and see that the greatest increases occur in the month of July. But what we also see in June, July, August is an emergence of some decreases in frequency over the Great Plains states, especially focused over the state of Oklahoma into Texas and then a bit into Kansas. Well, I mentioned that we also evaluated this using a very large category. Again, this would be 50 millimeters, and a moderate category, which is 25 millimeters. And what we see is a focus, especially in June and July, in the northern Great Plains. It's the highest change going through the summer. And then when we look at this moderate, what we see is an emergence of significant decreases, especially during the month of July. And this is something that has been mentioned in the literature on hail and climate change, and basically involves an increase in the level of the 0-degree isotherm in the vertical, and an increase in the height of this, or in other words, an increase in the melting level. And so that's one contributor. So hail that is of a smaller size has a greater opportunity to melt and fall as precipitation or fall as rain at the ground. But what we also see contributing to this is a decreased frequency in the initiation of convective storms that would then be more apt to generate relatively small hail. Well, we could look at changes in the hail season. And so this is another advantage of having kind of explicit representations of perils or hazards using this dynamical downscaling. And so what we've done, this is for this moderate hail category, the large hail category, and the very large hail category, is think about the nominal start to this season. There's really no start to the hail season, but we can use this definition by Harold Brooks to be the date on which 10% of the mean annual cumulative grid points is attained. And so just generally looking at the red, which represents the cumulative grid points for these different categories in the future, and the blue represents in the past. And what we see when we apply this threshold is a 16-day increase in the moderate hail category season, and then 9 days for the large and very, very large season for these categories. So essentially a week and a half earlier start to the hail season on average. Well, of course, we expect variability from year to year. And one of the hypotheses that we had going into this, and this is based on some work on observed data, is that there would be more interannual variability across the US on hail occurrence, as well as some of the other perils. And so the red here represents the annual number of hail days for the future time period. and the blue represents the annual number of hail days for the historical time period. And obviously you see that there's an increase for the future over the historical time period. But also when you look at the interannual variability, it would appear at least that the variability increases in the future. So you can imagine that if you're an emergency manager or decision maker or an insurance company, you would be very interested to know whether or not this is a likelihood in the future. So we can compute this. So here we're following some work that Mike Tippett did, and we're computing the difference between the number of hail days in consecutive years. So that the consecutive years are represented by I and I minus 1. And then we're going to define the volatility V as the standard deviation of these differences. And what we find indeed is that the volatility in the historical time period is less than the volatility of the future time period. And we can conclude that indeed there is more interannual variability, at least based on this perspective. So I do want to make a couple key points about this, that when we apply this downscaling, dynamical downscaling approach, it indicates the following: widespread increases in large hail frequency across much of the US, especially during spring, and widespread decreases in the moderate and large hail category, especially during summer. And that was fairly dramatic during June and July, especially over the eastern half or eastern third of the US. We also saw an overall lengthening of the hail season, with much as 2 weeks for the smaller hail categories and 10 days for the larger hail categories. And then finally, more interannual variability. So one of the hesitations about these results, and as you can imagine, reviewers were quick to point out, is that this is only based on one realization. The advantage of this dynamical downscaling approach is that it does allow explicit representation of these convective storms. So we know for sure that a storm formed, and we have this knowledge of convection initiation. And it also allows us to use storm scale variables. These are still proxies. We still don't explicitly represent hail sizes in a model that had has grid spacings of 4 kilometers, but we're at least using predicted variables. The main disadvantage, and again, this thread of compromise, is that the computational expense limits multiple realizations. This took a lot of compute resources to generate 30 years historical and past over the CONUS at 4 kilometer grid spacing. And so what this means is that we lack a measure of uncertainty. And so this is something that we're working on in trying to address. So those are the two questions that regards frequency. I want to spend a little time talking about intensity. And remember, this is my frowny face because this is the one that I'm particularly vexed about, and it's one that I get asked probably more often than anything else, especially in regards to tornadoes. So can we apply the same approach? Can we use dynamical downscaling to say something about changes in intensity of severe convective storms? And the answer is sort of. So we can use this and we can come up with measures of intensity. In some sense, we already did this with our different categories of hail size, and we can do the same thing with wind speed and so on. And what it will show us, we've done this, is statistics that basically tell us a future versus past. So more intense storms in the future relative to those in the past. But the problem, or at least the disadvantage here, is that it's really difficult to isolate cause and effect with this approach. What we really want to know is if we took some events and we put it somehow into the future under climate change, would that event become stronger? And if it did, by what mechanism, by what processes? So that's what we really seek to do. That's the answer that we really seek, is given a specific event or events, would those hypothetically be stronger in the future? So we can do this, as it turns out, by using a variant of downscaling. It's another modeling approach that's known commonly as pseudo-global warming, or PGW. And in particular, we're going to apply what we qualify as event level pseudo-global warming to distinguish what we've done and what other groups are doing around the country. This readily reveals causation. If we take an event and we put it virtually in the future, and that event changes, we know that we can attribute it to this imposed climate change. And the way that we're going to employ this approach is using a multi-scale, multi-model approach. Once again, we're going to use WRF, and this will represent what we will consider to be the regional modeling step. And then we're going to use an idealized cloud resolving, and in particular, a tornadic circulation resolving model that's known as CM1. And this is work that is in revision. So I want to give you just a little bit of primer on this pseudo-global warming approach, just to maybe help you understand what we're doing here. This basic approach follows what we published back in 2016 in Journal of Climate, and then in turn follows work that Gary Lackman has done, and then several others. And the basic idea here is that one conducts a control simulation of some historical event. And again, I emphasize that when we think about event, this is something that is lasting a day or a day and a half or something like that. And then we're going to resimulate this event with its 3D meteorological forcings, and here we're using some kind of reanalysis modified by a climate change perturbation. So this is just an example in terms of temperature, that we would have the temperature, the four-dimensional temperature distribution that we would use to simulate the storm or simulate this event. This is going to be equal to its four-dimensional temperature distribution that was used to simulate the control. So we will refer to this as its real forcing, and then some climate perturbation. We're going to refer to these as deltas. In this case, delta T represents some difference, some average distance difference in the future minus that of the past. And here what we're doing is we're actually coming up with a difference both in 3D space and in time. So our deltas have some time dependencies, especially relative to the time of the day, as well as 3 dimensions in space. So here's an example. So on my left here represents the delta fields at 700 millibars in terms of temperature. And these are from 5 different GCMs, so GFDL, IPSL, MIRAC, NCAR, and NORI-SM. These represent the changes in temperature, future minus historical, at this particular level. These are for some month, so these would represent the deltas at 700 millibars for the month of May across these different GCMs. You'll notice that all of the colors are warm, implying that these deltas at this level anyway are all positive. So we're warming whatever we impose this to. And so we're going to take these, and then we're going to add these to the time-dependent forcing of this event. So just as an example, we would add these in 3 dimensions to each one of these time periods. So we might simulate an event from 12 UTC on one day to 06 or 12 UTC on the other day. And these result in the PG modified states that we then use as initial and boundary conditions for our events. So I want to spend just a little bit of time talking about the kind of the potential issues, and these are questions that I typically get asked when I talk about this PGW approach. So let's respond to these right away, because I'm sure that these are burning in your mind. So what about the deltas? The first thing I'll note about the deltas is they tend to be relatively small, and more importantly, they tend to be balanced, as we showed in a JGR paper that we published last year. The implication here is that we can take these deltas, these climate change perturbations, and linearly superpose these onto a base state. They also don't result in significant adjustments. So we're not shocking the model in some weird way, and we've checked this in multiple ways. Let's see, and I said that they're balanced, and we've also evaluated this in terms of their geostrophic balance. The other aspect, the other question that we typically get is it regards the spin up time. So in these simulations, as anyone knows who have done real case simulations with WRF as an example, we allow for some spin up time, 6 to 12 hours, for the model to generate a mesoscale spectrum. And so we want to make sure that we have that. But what we don't want is a spin up time that lasts for days for these, because what will happen is that we'll start to develop error growths that are going to essentially ruin our simulation. So we want to have the spin up time, but at the same time we want to minimize the time between when we initialize the model and the period that we're most interested in. Here would be tornadoes. It might be when the hail is generated or something like that. And then finally, we're only interested in the model response to the climate change imposed via the deltas. So we have done lots of experiments with different parameterization schemes, which microphysics scheme, which boundary layer scheme, and so on and so forth. Those we used to come up with the best model representation of the historical event, the control. Once we've established that, though, what we want to know is how that simulation responds to the climate imposed by these deltas. We have 16 different delta formulations. So there are 5 different GCMs. Each one of these GCMs are used to come up with a different way of computing the deltas. And then we additionally have a composite. These compose an ensemble. And from this ensemble, we're able to evaluate the kind of the range of responses owing to the climate change. Okay, here we go. All right, here we go. So we chose 2 representative cases, and I'm gonna come back to this because this is another question that we get and another criticism of this approach. But our idea here was to use representative but contrasting cases to address this question of whether the intensity of a contemporary tornado would increase under some imposed climate change, the deltas. And so our 2 cases are what I'm going to refer to as the cool events, because it occurred in February in the Southeast, or in particular Hattiesburg, Mississippi. This includes an EF4 tornado that occurred in that area. Then the infamous Moore, Oklahoma tornado event of 20 May 2013, which I'm going to refer to as the warm event. And this includes the EF5 tornado that occurred near Moore. And our hypothesis, based on the meteorology and of these 2 different events, is that the magnitude of the response of the cool event to this imposed climate change, this pseudo-global warming, will be larger than that of the warm event. All right, so I mentioned we're using WRF, and this is a later version of WRF because this is a more recent study. We do use the NAM analysis for our initial and boundary conditions. These show the 2 domains for the warm event and for the cool event. We have a 3 kilometer and an embedded 1 kilometer horizontal grid spacing nest. Our analysis is going to be based on these inner nests. Both of these are initialized at 12 UTC and then run for 24 hours. And as I mentioned, we did a number of different simulations to come up with the domain and the grid spacing and the parameterization schemes, the model setup in general that exhibits both qualitative as well as quantitative similarity to the actual events. So I'm going to use a couple metrics here in terms of how we quantify the results. I'm going to talk about consistency, and I claim consistency if 75% of the ensemble members exhibit the same sign and the percentage change. And here this is all going to be PGW relative to control in some given metric. And then I'm going to talk about robustness, and here I will claim robustness if the signal to noise ratio in some metric exceeds 2. And here the signal represents the mean value across the ensemble, and the noise is the standard deviation. All right, well, how about some results? So I want to start first by talking about the intensity of the storms themselves. And once again, these are all going to be given as percentage change relative to the control. We'll start by updrafts. And in particular, we're starting by occurrences of updraft cores, individual grid points that have speeds of 25 meters per second or more. And this represents a high percentile value of updraft speeds at individual grid points. And what we see for the warm events is that it's a consistent, robust result, that there are more updraft cores, more strong updraft cores in this event relative to the control. So in the future, what we also see, interestingly, is that there are many of our ensemble members that actually have peak updrafts that are weaker than the control. And this is a bit counter to our expectation, because when we look at the environmental conditions, in particular, when we look at CAPE, the CAPE is higher for the warm events in nearly all the ensemble members, but yet when they are actually realized as convective storms, some of the updrafts are actually weaker than the control. What about our tornado proxy? So I'm using this in quotes because what we've evaluated is a parameter known as updraft helicity. Updraft helicity is a vertical integral of the product between the vertical component of vorticity and the vertical component of velocity, W times zeta. These are integrated from a level 2 kilometers above the ground to 5 kilometers above the ground. And what they tell us is at individual grid points, how much the updrafts are rotating, how much the updrafts exhibit rotation. And for this warm event, what we find relative to the control is that the occurrence of 95th percentile values of this proxy are inconsistent. A lot of them are fewer than what we find in the control. We can increase that threshold to the 99.9th percentile. We see that there's some consistency in the sign, but it's not robust. So one of the conclusions that we have immediately is that this warm event, even though it has a tendency to have more stronger updrafts than in the future than in the historical time period, in terms of realization of rotating cores, which then could contribute to tornadoes, they tend to be weaker. And I'll mention here that one of the criticisms that we've gotten from this work so far is the use of this particular metric. And so I've spent the last couple of weeks looking at other metrics that are near ground, and the results are the same. That we still get fewer tornado proxies and fewer strong tornado proxies in this warm event. What about the cool events? So we do the same thing where we're looking at the numbers of strong updraft cores. Remember that this event occurred in February, and so we're seeing a pretty significant increase in the number of strong updrafts throughout the domain. What we also find is that every one of the ensemble members has an updraft that is stronger than that in the control. So that's a consistent and robust result. The other key point here is that these are updraft speeds that are 40 plus meters per second, which this is Mississippi in February. So this is something that we would not tend to see in normal times and during the month of February in the Southeast US. What about rotating cores? We're using the same idea of this metric that's based on this parameter called updraft helicity. But once again, the results are the same if we use a different metric that's based on vertical vorticity near the ground. And what we see is consistent and robust increases in the occurrence of these rotating cores and consistent and robust increases in the occurrence of intense rotating cores, which we relate to tornado proxies and intense tornado proxies. And what you also see across all of these is that the mean values in the percentage changes are much greater during this cool season event than during the warm season event. So some key takeaway points here is that we see relatively fewer weak events, but more strong tornadic circulations in this future realization of the warm event, and more numerous and stronger circulations for this cool event. And then as hypothesized, the magnitude of the response was much larger for this cool season event than for the warm season event. One of the issues here, though, is that we still haven't really answered this question of changes in intensity. And I say this because when we look at the individual storms across the different simulations, there's not necessarily a one-to-one correspondence. So there might be one storm that in the control simulation best represented the Hattiesburg tornado. In the future simulation, we might not see an exact storm that was in that exact location. It may be displaced in some other, or maybe there's two. And so it's hard to answer that question. So what we've done instead was apply an additional step, and this is this cloud resolving modeling step. What we did was draw profiles from our WRF simulations, both in the control and PGW simulations, and use these as initial and boundary conditions in our cloud resolving simulations. We can do these at much higher resolution. So here, these are done with 64-meter grid spacings. And we also initialize the model such that there's only one storm, and then we can do a head-to-head comparison. So the main metric here is tornado power that is well resolved. And when we look at this warm event, when we evaluate tornado power, which takes into account both the speed and the size of the vortex, the results are yet once again inconsistent, but we do see some increases. When we look at the core wind speeds, there are some that are less, there are some that are greater than the control, and then we look at the core width, and they're consistently negative. In contrast, when we look at the cool events, that this is a consistent and robust result. One ensemble member has less tornado power, but all the other ones have more tornado power. And then similarly, the ensemble members have stronger mean core wind speeds and mean core width. And so what we can take away from this is clear indications of increases in this tornadic circulation intensity with this cool event, and confirm our hypothesis regarding a relatively larger response to this event. I want to circle back just real quickly to this idea of environment, because one may ask, could we just have anticipated this by looking at environmental conditions? And the answer is partly yes. We can evaluate a parameter that's known as the significant tornado parameter, which accounts for CAPE and this SO6, but also in a parameter known as convective initiation, or convective inhibition rather, and then another measure of vertical wind shear. And what we see is based on the environments that we just used for those cloud resolving model simulations, that this significant tornado parameter is greater on average and it exhibits a greater increase relative to the control environment, and the warm season environment represents a decrease. So I want to make a concluding statement on this work. What it provides is at least justification to argue, let's go back to that future tornado intensity may increase in response to climate change. What we're not arguing is that all tornadoes will be stronger in the future. And indeed, heterogeneity within the atmosphere will still persist. But what we see is that because cool season environments, as we just showed, tend to be characterized by relatively large vertical wind shear and relatively small cape. If we increase the cape and decrease the vertical wind shear just a little bit, we still have a highly favorable environment. Okay, I'm gonna end here with a couple unresolved issues and some future directions. One of the issues that we have with this PGW approach is how to come up with a convincing number of events. I showed 2 in the paper. We present 2 more, so that's 4 cases, but maybe that's still not enough. It's not enough for many people. So what's the right number? We haven't figured that one out yet. What I can tell you is that this approach is really well suited for attribution work, and it's something that we're working on right now. Given an event, perhaps maybe something that occurs tomorrow in the Southeast US, to what extent can we attribute the intensities of those events to climate change? This dynamical downscaling, as I alluded to, one of the issues that we have is the inability currently to generate a sufficiently large ensemble of CONUS scale convection permitting multi-decadal simulations. And so that's an issue that we face, and we have some alternative approaches that we're working on right now. But in order to really move this approach forward, we need an ensemble. And then finally, this GCM analysis. I kind of feel like we've exhausted, or at least we're getting to the point where we need to go beyond these environmental proxies. And so one of the things that we're working on right now that extends some work that Julian Brimlow did with hailcasts and basically driving this offline hail growth model using GCM data. Okay, well, I should probably stop now. And I thank you for your attention. Once again, John, thanks for the invitation to be here today. And I'm happy to take any questions that you might have.
Thank you, Dr. Trapp. If anyone has any questions, you can go ahead and raise your hand or unmute yourself or type it in the chats, or just ask me to unmute you in the chat. Oh, go ahead, Claudia.
Hi, can you hear me?
Yes.
Well, thank you for this interesting talk. I was curious about your answer to question 1 that you said was a non-starter, and then your final comments here about the value of this type of analysis that you presented for attribution. So did you say it was a non-starter because you don't like the use of the term cause, or because it would take too long to actually run this analysis to answer the question of the journalist, or why was it a non-starter?
So a non-starter is because these events existed in pre-industrial times. And so to say that we have
it's
tornadoes because of climate change, it's not the root cause.
Okay.
So that's an answer that we try to communicate.
Okay. Yeah. Thank you.
Yeah. And so I'm not sure if I understood the second part, but the attribution part is again, I think this is really well suited for to address those kinds of questions, and it's something that we're working on.
Mm-hmm. Yes, I agree. Thank you.
Mm-hmm.
Any other questions? Claudia, go ahead.
If nobody goes, I have another one that is completely unrelated. So you were presenting your results in I think it was the paper with Noah Diffenbaugh, and I think that was a scenario with RCP 8.5, and it was the end of the century.
Yes.
I was wondering if you have a sense of how this type of change behaves as a function of global warming values or levels.
Yeah, so there's a really nice paper. So I said that this is a little bit dated, or at least the work was dated, but the narrative is consistent. But there is a paper by Laporte et al. That this was in Earth's Future or AGU Advances, one of the two earlier in 2021, which they use CMIP6 data, and they did look at different scenarios and and at different time periods, I believe. I know that at least they looked at different scenarios, and we chose end of century, worst case scenario, because that's where we thought we would get the strongest signal. And indeed we have looked at mid-century, and the signal is still there, but it's not as strong. There's another paper that Walker Ashley and his colleagues just published in the Bulletin that shows a similar response, and they use dynamical downscaling. So it's there. It's just not as dramatic. In the Diffenbaugh paper also, as in previous work, that we show some time series, and you can also get a sense of the response, at least in terms of end of century and mid-century, from those time series.
Thank you.
Mm-hmm.
Thank you. Liang, you can go ahead.
Hi, Bob, thank you for making the presentations great. I really welcome you. One question, as we all know, the GCM and the regional model alike, they have pretty much a very large bias in the simulating these large scale and massive scale circulations. Mm-hmm. So how is that the bias actually will affect the future projection which you are presenting?
Mm-hmm. Yeah, so I will say that those runs that I showed were not bias corrected. The argument is that if there's a bias that applies to the historical time period, that bias is the same, or the model's biased in the same way in the future. So that if you look at the differences, that we essentially remove the bias. So that's the one way of explaining that. But yeah, in the end, if I did this in the future, and we're doing some regional climate modeling work in a separate project, that we hope to use some kind of bias corrected data sets.
Yeah, so because this is a very interesting topic, as in our group, we have done quite a few studies to try to say that if we have a regional model that have much more closer to the observation, then using the same regional model to produce the future projection, like for example, these extreme events like precipitation or so. The differences between that, the bias, the improved model versus non-improved model results for future change is significant, very, very large.
Okay, right.
So I think this may be important, particularly when we look at this extreme event like a tornado. I think that is very much strongly depend on where the mesoscale circulation, the bias look like.
Yep. Well, and once again, it goes back to that comment that I made about having ensembles, and so yeah, I can do some bias correction on a GCM and then do dynamical downscaling, but I really want to know how that's varying across the different GCMs that I'm downscaling.
That's true. Thank you very much.
Yeah, thank you.
Any other questions? Okay, well, unless I am interrupted, which please feel free to do so, I think we can conclude today's talk. Thank you so much, Dr. Trapp, for coming to talk to us today. This was a great talk. And thank you everyone else for showing up and participating in another Essex seminar. I hope you all have a wonderful week. And we will continue our seminar series next Monday. Thank you.
Okay, thank you.